So it's my pleasure to welcome Professor Amir Yacoby from Harvard. He will talk about correlated electron phenomena in suspended graphene.
So to give me the opportunity to present to you today some of the recent work we've been doing in exploring correlated phenomena in single and bilayer graphene. One of the unique features of graphene is that it has two internal degrees of freedom, electron spin, and the other one is the pseudo-spin that corresponds to the Valley degeneracy that we've heard already introduced this morning. And as we've heard many times today, what degeneracies offer is the ability to add charge into the system without paying an extra kinetic energy. And so this suggests that extra degeneracies may lend themselves to having stronger or interesting correlated phenomena. And that's what I'd like to explore today, mainly the interplay between spin and valley and how they translate into fractional quantum Hall states in graphene. So what I'll talk today, I'll cover a few topics of the recent experiments that we've done, some published, some unpublished. I'll show that we now see very, very fine fractions in single-layer graphene. The measurements are done roughly at 400 millikelvin. So this is, I think, great indication that graphene is moving towards the very clean limit. We see many, many phase transitions. In fact, each one of these fractional quantum Hall states exhibits a phase transition that has to do with internal ordering of the internal degrees of freedom. And we see signatures of these phase transitions persisting all the way very close to filling factor a half, that essentially corresponds to 18 or 20 composite fermion Landau levels occupied. And I'll describe that in greater detail. We also see quite a few fractional quantum Hall states associated with four-flux quanta, and I'll describe those as well. There's some interesting symmetry breaking and symmetry preserving states. So in certain ranges of filling factors, we see conventional sequence of fractional quantum Hall effects, and others we do not see them, and I'll describe the phenomenology and give some suggestions of where things are coming from. So the work that I'll talk about today were carried out by two graduate students, Ben Feldman and Andre Levine. We've collaborated, benefited from Benjamin Krause, who spent 6 months in our group, from Jürgen Smet's group, and we've benefited tremendously from discussions with Bert Halperin and Dima Abanen. So I'd like to start by saying that our theory friends give us experimentalists quite a bit of, they trust us too much. I'd like to show here one paper published this summer from Ashwin's group, saying basically that in a strained graphene layer at fractional filling, in the absence of an external magnetic field, if one is able to fill it to fractional filling, one should expect interesting fractional quantum Hall states in the absence of magnetic field that spontaneously break time reversal symmetry.
It doesn't say, but also in the absence of disorder.
Which is the topic of this talk. We're going into the direction of the absence of disorder. We heard Adi give a talk yesterday about fractionalizing Majorana fermions, and they say the fractional quantum Hall state in graphene might be promising candidate for realizing such a system, since the magnetic field in which these states can be observed might be very low. So, they trust us greatly, and what I'd like to do is maybe use this talk to give you, to some extent, a status or a sense as to whether these kind of ideas are really crazy or can in fact, in principle, or maybe practically be realized. So, as I mentioned, graphene has both spin and valley degeneracy, and once one applies a magnetic field to the system, one generates Landau levels, and one of the unique features, both in monolayer and bilayer graphene, is that the lowest Landau level sits at the Dirac point, and because of the double degeneracy of spin and valley, one ends up with a fourfold degeneracy. And in the absence of any interactions or symmetry breaking terms like Zeeman terms, of course, if one were to position the Fermi energy in the middle of this Landau level here at zero density, then each one of the 4 Landau levels would have been occupied to half its capacity. Of course, interactions would favor organizing the charge in these layers in a different way, preferring to fill up entirely 2 levels and leave 2 empty, which basically is known as quantum Hall ferromagnetism. And given the 2 internal degrees of freedom, the spin and the pseudospin, and the pseudospin both in single layer and bilayer graphene in the lowest Landau level could either be thought of as a degree of freedom associated with a valley, but in the lowest Landau level it could also be thought of in real space as a degree of freedom that identifies the sublattice. And I'll mostly discuss things in terms of sublattice just because it gives us a real space picture rather than a momentum space picture. And I'll use red arrows to describe pseudospins, namely when all the electrons are sitting on one sublattice, sublattice A, then this pseudospin will be pointing to the north pole, B would be south, and somewhere along the equator would be some well-defined superposition, and the same thing with the spin, and the spin typically will be pointing in the direction of total magnetic field in the case when there is some parallel field to the layers. So I've indicated here for the nu equals 0 state, so there is a quantum Hall state that emerges at filling factor 0 when the density is 0 in the system because of this quantum Hall ferromagnetism. Symmetries are broken spontaneously, but because of this large phase space, there are actually quite a few possibilities for what is the underlying order that describes this nu equals 0 phase. And the reason I'm going to spend a little bit of time about nu equals 0 is when I'm going to talk about fractions, we're going to be building off to some extent on top of that full 2 levels. We're going to be filling up this empty state with fractional states, and it might give us a little bit of intuition to think about what is the underlying nu equals 0 state, although it does not necessarily have to be related. So there are 2 possibilities for these 2 Landau levels to be filled. One is where these 2 Landau levels, one corresponds to pseudospin up and pseudospin down. This means that the system is valley or layer or sublattice unpolarized, and the remaining degree of freedom for the 2 layers is spin, and there are quite a few possibilities. You can imagine, for example, that in the presence of a very strong Zeeman field, then all the spins would like to be polarized. This would be a ferromagnetic state. But it turns out that energetically, one could favor, under certain conditions, from a antiferromagnetic states when the Zeeman energy is not that large. And this is something that is really taking advantage of the full SU4 symmetry of the underlying internal degrees of freedom. In the intermediate regime, as Zeeman is increasing, one can end up with something that's called a canted antiferromagnetic state, where the spins just cant a little bit in the direction of the total field, but still have a lot of this antiferromagnetic nature in place. Alternatively, one can consider these 2 layers where the ordering occurs in the valley degree of freedom, which means that now we fill up entirely the 2 spin Landau levels, so spin up and spin down are now entirely full. And again, you can have a variety of possibilities in this layer polarized or partial layer ordering state. One can imagine a charge density wave where all the electrons, both spin and up and spin down, are sitting on one sublattice, on the A sublattice, for example. One can imagine that they're all sitting on some well-defined superposition of A plus B. This is known as Kekule distortion. There are particular directions along the crystal where electron-phonon interaction would favoring distorting the crystal to give an orientation of this pseudospin to be in the plane. And of course, one can imagine something intermediate, which is analogous to the canted antiferromagnetic state, but now playing with a layer degree of freedom. Now, one of the nice things about bilayer graphene is that effectively the 2 sublattices, the A and B sublattices, sit on different layers, and so one can externally affect both the spin degree of freedom using a Zeeman field, but one could also externally affect, break the symmetry between sublattice A and B, because now they're separated between the 2 layers. And indeed, a transition from something that is partially valley ordered to partially spin ordered has been seen and is being explored further. But these are experiments that we've done a couple of years ago, where one is looking at the conductivity of the nu equals 0 state, which is very, very low. It's typically gapped. But now you have two parameters. One is a magnetic field, which in principle will try to favor spin ordering. The other one is an electric field, which will try to favor pseudo-spin ordering. And you see that there is a phase transition that occurs, which takes you from what is known as a partially layer polarized state, which is shown here, to the canted antiferromagnetic state, which is shown here. And there is quite a good, at least qualitative, correspondence between theory and experiment. In fact, if one wants to try and really push this state at low electric fields to the ferromagnetic state, where all spins are fully aligned with a magnetic field, just increasing the external magnetic field perpendicular to the layer will not do it, because that essentially enhances both the spin, the Zeeman term, but also the lattice asymmetry. And so if one really wants to favor the ferromagnetic states, one needs to apply a magnetic field in the plane, so only to affect the spin. And these are experiments that are currently done. I think they're still unpublished, but Philip Kim's group is now beginning to see that this canted antiferromagnetic state is slowly turning into the ferromagnetic states as a parallel field. Oh, they're just highlighting this phase transition. This is just the max. It's just the guide to the eye.
The canted antiferromagnetic phase is coming to an end. It's no longer what is beyond the red dashed line.
So this is conductivity, and we don't really understand. So I mean,
not really do a one-to-one correspondence with the phase diagram.
No, the phase diagram, it is a one-to-one correspondence. The question is, why is there a peak in conductivity at the phase transition? This is something that we don't exactly understand, and why this peak in conductivity is weakening as magnetic field increases.
Then maybe I'm not following something. Here, the candidate phase goes all the way to zero electric field. There, you have a dashed red line.
So here, the canted antiferromagnetic phase does go all the way to zero magnetic field. In fact, the canted, zero electric field. Here, you see these lines do not extrapolate to zero electric field. So there is a finite region for which this canted antiferromagnetic phase lives near zero electric field. And this is experimentally seen. In monolayers, to control the pseudospin is not so easy. You don't have this external knob that could favor sublattice A versus B. And there's a different way that one can imagine trying to identify what is the underlying order, and that is through just the simple transport experiments where it turns out that the way these Landau levels that I've described so far in the bulk disperse as one reaches the boundary of the sample. And so depending on the type of ordering, for example, the antiferromagnetic states, it turns out that for a particular edge, and this calculation was carried out by Kharitonov, you see that a gap is fully open, and this would give you indeed zero conductivity at the nu equals zero phase. But as you increase your spin polarization in the system towards the ferromagnetic state, in the limit where you fully align the spins, it turns out that the edge dispersion has this kind of quantum spin Hall flavor, and the conductivity should be 2 e squared over h. For the valley ordered states, it turns out that all types of valley ordering will always have a gap. And so this is the only state that would have a finite conductivity, even though you're at zero density. It should have 2 e squared over h conductance. And so the fact that people do not see it just with the application of perpendicular magnetic fields suggests that it's very likely not this phase that nu equals zero corresponds to, but which one of the other ones is not really known. I'll address that when I come to describe some of the fractional quantum Hall states that we are observing. But it's very likely not the, sorry.
Conductance measurements that you showed a moment ago, those are all two-terminal conductance measurements in the Hall bar?
Yeah, they're two-terminal. You see a similar thing, and four-terminal is just harder to do. Two-terminal typically are much nicer measurements on suspended devices. Yes, I think Philip Kim has done Corbin, not on suspended devices, and I think just seeing various broken symmetry states, but has not done any, systematic study of electric field. So on monolayers, another indication that it is not the ferromagnetic state that one has in the presence of just a perpendicular magnetic field has come from recent work in Kim's group, where one applies a parallel magnetic field, now trying to polarize the spins, and indeed one sees that the activation gap associated with the nu equals zero state is coming down as one applies a parallel magnetic field, as if a gap is closing, again, very consistent with this picture of the edges. And in fact, I think that in Pablo Llorilo Herrera's group at MIT, they're beginning to see also a saturation of conductance at nu equals 0 as they apply a large parallel magnetic field. So I think this picture is beginning to make sense. But the focus of this talk is not the integer quantum Hall effect, is in fact the fractional one. And I'd like to introduce a little bit of terminology that I'll be using here. And this is not graphene. This is one of the nicest pictures of fractional quantum Hall effect in gallium arsenide.
Could I quickly ask you a question? You don't need to go back.
Yeah.
Is there any hope of, I'm kind of biased about the Canton antiferromagnetic phase. Is there any hope of doing some kind of spin polarization measurement, a pseudo spin polarization measurement like it was done for gallium arsenide to really definitively establish that there is a Canton phase like the group from Japan did? Because, transport can only be consistent, but if you directly see that, is there any hope in graphene for that sort of experiment?
So I think in principle, yes. And I think these kind of tilted experiments where you basically should see a second order phase transition. So as you're applying the parallel field, you're canting the spin. At some point, they will jump to be fully ferromagnetic. So I think these but again, in transport, thermodynamic is, it's hard. Yeah.
Like Kumoda and those guys, the way in gallium arsenide reaction.
Carbon 13 bilayer.
Yeah, maybe. I mean, natural, of course, carbon, you don't have much nuclear spins, and I don't think people have seen any hysteretic type behavior in any of the quantum Hall phases. So I think that that would be a very weak effect. So what I'd like to do is basically just remind everybody of the composite fermion picture, which is a very simple way of discussing fractional quantum Hall effect, where one thinks of new fermions. These are electrons that are bound to two flux quanta in such a way that when the magnetic field corresponds to half filling, all the magnetic field is absorbed in these composite fermions, and the system displays a Fermi surface. Once one moves away from that filling factor 1/2, one basically generates integer quantum Hall states for these composite particles, and these are the fractional quantum Hall states, and they're very simple correspondence between the filling factor of electrons, nu, and the integer quantum Hall state of these composite particles. So P basically enumerates how many composite fermion Landau levels are occupied. So for example, when P is 1, depending on whether you go left or right from nu equals 1/2, you see that filling factor, electron filling factor of 1 and 1/3 corresponds to a one integer quantum Hall state of composite fermion. So it's basically the numerator of the fraction that will enumerate how many integer quantum Hall states are occupied for these composite fermions. And you see many, many more fractions now. So this would be a 2/5, 3/7, 4/9, 5, 6, 7, 8. So these are the number of composite fermion integer levels that we're seeing. But in addition, you see that each one of these fractions has some negative feature here that's cutting across, where the gap meaning an incompressible feature, suddenly collapses and then reappears again. And you see it for each one of them over and over again. And by the way, blue here means negative. So this is a negative compressibility. Negative compressibility is something that you cannot understand from single particle physics, because that's just the density of states. You do not have negative density of states. This is an interaction effect. And you see that there is something very profound, a negative density of states that cuts across each one of these fractions, and the gap collapses and reappears.
So is it indicating instability?
It's indicating a phase transition. You could look at it, zoom in. This is 4/7. You see this incompressible gap, and then it cuts off by this negative feature and then reappears again.
The remarkable thing is that it cuts through.
It cuts through.
If you saw negative compressibility on each side, they parallel, you wouldn't be surprised.
So look, this is all blue. This is all negative compressibility. This is not surprising. You've studied that for many, many years. This is quasi-particle correlation. But it's cutting across. It's very profound. And, we've studied in the past gallium arsenide, nu equals 2/3 phase transition. And you see 2/3 is very complicated. There is a negative feature cutting across, but it's just much harder to see because of all the localized states. Now we could see it all the way up to these very fine fractions, very nice negative compressibility that cuts across. And so
It looks like a quantum critical point. If you go from one quantum Hall state to another.
that's right. And that's the way I'd like to describe it. And so these phase transition come about from the internal degree of freedom of these composite fermions. And here we have, again, there are two internal degrees of freedom. So we can imagine let's think again about the filled state. And let's, for example, select a filled state, which is this Kekule-type disorder. So there's the two Landau levels that have been filled are polarized somewhere in the pseudospin space, and this means that it's a spin-neutral state, a spin-singlet state. That's a nu equals 0 phase. And then we're filling up the empty Landau levels. They're both going to have, regardless what we select, they're going to have the other pseudospin state. So we have a spin degree of freedom to play with. Alternatively, if our ground state was the ferromagnetic state, spins polarized, then we would have the valley degree of freedom to play with. So if we want to write an energy for these composite fermions, we can describe it in terms of some effective cyclotron energy for these integer composite fermion Landau levels. So there's an omega c star here, and I'll tell you what it is. But then there's a Zeeman term if this was spin, or there is a pseudospin energy, which turns to be also linear in magnetic field, which would correspond to the valley. And we don't know which one it is, but it doesn't matter. In this model, there's just going to be a linear B term together with this cyclotron term, and we're going to see how these two energies compete. Now, since these are composite fermions, the cyclotron energy has a magnetic field effective B star, which measures magnetic field from filling fraction 1/2, and it has an effective mass, which is, of course, we're in the lowest Landau level. There is no mass, so this is an interaction term, and that scales with the square root of magnetic field. And so there is a competition as you change magnetic field between states that disperse linearly in magnetic field and things that disperse as the square root of magnetic field. Yeah. What comes out of quadratic? So this is not single particle. This is already interaction. So here the mass is just square root. The mass is a measure of the interparticle separation. Square root B. Yeah. So if you just plug these two in and you look at what the energy for a Landau composite fermion state with integer p, it would have a square root B term and a B term. And of course there is a plus and minus because the Zeeman or the pseudo field would either go up in field or down in field. There's one that is gaining energy and one is losing energy. And if we just plot this thing as a function of E over square root B, we get a constant plus something that's linear in square root B. So this is what...
The value term will be also linear in B. Are you just assuming?
No, it's expected. I mean, the reason is that the valley term...
Okay, don't explain, but there is a reason to expect.
Yes, and it's expected to be linear in B. Yeah. So here are these for p equals 1, 2, 3, and so on, but for the negative sign. And this is as a function of square root b, so these are straight lines. And for the positive one, they're going upwards. And you see there are a lot of crossings. And so now we can try to understand what goes on. Suppose we want total integer composite fermion filling of 1. This would correspond to either filling fraction 1 or 1/3. And we see that regardless, if we just keep p equals 1, we see that we are in a spin-polarized phase. There's nothing interesting happening. This is the 1/3 state or the nu equals 1 state. Nothing interesting is going to happen. But if p is 2, and this corresponds now to 2/3 or 2/5, you see that something interesting is happening. In low magnetic field, the system prefers occupying both spin states, but only one composite fermion orbital state. But in large magnetic field, it would rather spin polarize and occupy two composite fermion states with the same spin. So there will be a phase transition appearing at some magnetic field, and you see that when p is 3, there are going to be another phase transition at some other magnetic field, and for a large magnetic field, in fact, there are going to be a bunch of those. At very large magnetic field, the system will eventually be spin polarized or valley polarized. I have not specified which one it is, and in fact, we don't know. But in this very simple picture, you see that we expect these kind of phase transitions to emerge.
Amir, this sounds very analogous to gallium arsenide.
Yes. Even you don't have to tilt. I mean, you see this phase transition at 2/3 in gallium arsenide.
Composite fermion levels around 3/2, for example.
Yeah. Yeah, that's right. Yeah.
You tilt, so you can independently change Zeeman and correlation.
Right. And then they will cross and cross and cross. Yeah.
These are, I mean, this is Cohn-Parkes thesis. These are spin polarization transitions of composite fermions.
Yes. Or valley polarization. We really don't know. Yeah, but one of them. Yes. Correct.
It's spin polarization transition of composite fermions.
That's right.
You can just use non-interacting language, which is what you're doing.
Yes.
To understand how
So-
the thing will take, right? That's
Yes, that's correct.
And the middle is the Fermi, composite Fermi C.
Sorry?
Right in the middle.
In the middle, it's the Fermi C, right. So we can now go back and look at this data. Now, instead of plotting filling factor here, nu, I'm going to plot p, the integer, associated with the composite fermions. Okay, so that's the relation between nu and p. And you see that when we do this transformation, so now the x-axis here is p. This is the number of how many integer Landau levels of composites we're filling. So this would be 2, that's a 2/3 state. This is 3, the 3/5, 4/7, 5, 6, 7, 8, 9. You see that we are basically seeing really delicate fractions, but more importantly, you see that these blue features that cut across each one of these phase transitions, they persist, and they persist up to very, very large values of p. And these are not Shubnikov-de-Haas oscillations that you'd imagine you would have around filling factor 1/2 of composites, simply because if you just go along a constant filling factors, there aren't any Shubnikov oscillations when the filling factor is constant. So these are reminiscent of these phase transitions that are persisting now to integer composite fermion fillings of very large number, 20, really coming very close to filling factor 1/2.
sense, right, the blue regions are where you say you have this negative compressibility. In some sense, that's the absence of these effects, these fractional quantum Hall states. It's not obvious that they're special.
So you'll see it in a minute. It's
The background compressibility is negative everywhere.
yeah. So here there's an additional effect, and I think, sorry?
This is more negative than it is in sort of the background.
It is more negative. It's much more negative than the background. Much, much more negative than the background. Oh, yeah.
Well, blue is blue.
No. This is filling factor 1/2 is negative compressibility as well. So you see, this is negative. Everything here is negative. These are very negative. Okay, you'll see where it comes from. It comes from this very simple composite fermion picture. The qualitative understanding comes from that. 0 minutes. Let me wrap up very quickly, if I can. So you can take that same model that I described and now just calculate how the energy changes with density and compute a compressibility. And this is what comes out. And you see it generates, blue is blue, it's negative. This is negative compressibility. And you see the reason is simply that on certain regions here, the system has a positive slope and other regions has a negative slope. These negative slopes are the negative compressibility region. So qualitatively, I think this picture produces these phase transitions very nicely and the blue features that are cutting across. There are many things that I don't have time to discuss. There are many things that deviate, and this composite fermion picture doesn't take into account exchange and many other things. But the qualitative picture, I think, is nicely emerging.
So they are like the two-phase region, coexisting.
Yeah, so at the transition, it's exactly a two-phase region. There are coexistence. No, the blue region is not. This is a well-defined phase. It's only here that you have coexistence.
It's kind of interesting that in gallium arsenide case, occasionally where these transitions occur, the resistivity gives you pretty good evidence that there is phase.
That's right.
Almost like it doesn't happen here.
You don't. Well, here I don't know about resistivity,
I
but
understand, but I'm looking at one of those red lines coming up, and then the blue thing appears. It's not like the two red lines kind of separated simultaneously exist. It's slightly different filling factors away from it.
well, when you zoom in, it looks a little bit like that. But certainly the transport does not show any signatures of this very strong negative feature, and why it's so well confined here. We don't understand many of the things. Okay, just maybe if I may, 2 more slides I'd like to show. One is this previous picture, this composite fermion picture, assumed that we have an interaction energy that scales with square root b, and then there is some linear b term. Note, this is the energy gap of 1/3, and 1/3 you'd expect, okay, it has no Zeeman term. It should only be square root b, but in fact it's linear in magnetic field. So essentially, we don't understand why the energy of the 1/3 gap is just straight on linear. And this basically says that our model is you know, it's not a valid model to some extent because it should have been a square root b. So this is one big thing we don't understand. The other thing that I just want to point out before summarizing is just to highlight that we now see very nicely 4-flux attachment composite fermion states. This is the 1/5, 2/9, 2/7, 3/11. We see it also between filling factor 1 and 2, 6/5, and so on. So I think that, and you see again a lot of these indications of the blue features, which now we know to identify as precursors of phase transition. So these are things that later on, if we could push the magnetic field, we'll see them cross at some point through the system. So with this, let me just summarize. I think we're at a nice phase where graphene is cleaning up more and more, and we're seeing a lot of these correlated phases, and hopefully more interesting physics will come. Thanks.
One is, what is the mobility of this sample, and nominal mobility of this double anneal, the best sample that you showed?
I don't know to answer that question. This sample actually has a certain region that's a bilayer, a certain region that's a monolayer, so that we could study both of these systems. If I were to show you transport, it looks completely ugly.
Really?
So
Field transport looks ugly.
Very ugly. It has a nice Dirac peak, and if I were to extract it, maybe I would say it's a few tens of thousand. But
a few tens of thousands.
Yes.
It's not okay.
Yeah.
So something is going on.
About a micron or a micron and a half away from where we're scanning. And we've scanned towards the interface. We've actually looked at bilayers a lot.
But when you're doing transport, you're going through both?
Yes, but in parallel. That's right.
And a quick comment on which I have no insight. Your data may have information about a subject in which gallium arsenide physics is not telling us something, which is interaction between composite fermions themselves. You know, this is an unexplored territory. This picture of Jainendra is a little bit a cartoon picture. Composite fermions don't interact, right?
Mm-hmm, exactly.
And you are using composite fermions as a non-interacting object too. But you have enough data there that we may have some information about this weak interaction between the composite fermions.
Mm-hmm.
Okay. Last question. Very short question. You showed that annealing gets rid of the localized states. What are these localized states in graphene?
Well, so you're asking, I mean, the localized states are basically just density and homogeneities in the sample that when you're close to an integer or fractional filling creates an incompressible region that surrounds a compressible region. And so you have these pockets of charge that give you charging phenomena that look like Coulomb blockade, and that's why they're running parallel to filling factors. The origin, what is the source of disorder? It's probably crap from the processing. It's adsorbed stuff. And the reason things are improving, so when we're annealing, basically the sample is heating up to a few hundred degrees. And that process, we're probably desorbing a lot of things that are bound to it and improving. And you still see, I didn't have time to show it, but if you move from one location to the other, you see that there is still quite a bit of disorder, but on larger length scales.
Since we have overshot nearly 10 minutes, we will stop questions here and thank Amir for an excellent talk. There is a small memento from the organizers.
Thank you very much.